Okay. Additionally, these cells grow along the computational domain. If we mention this is our required part and we want only refinement here, it refines only the particular cell zones around here. That means it can decrease the cell size much more smaller like this and can refine here much more. Where external to this, it can keep those cells much larger. So these capabilities are all predefined in the ANSYS software. That's why it is a commercial one. So it has the capability to understand what is our required component. So at that required component, if a cylinder is your required component, there it creates a small mesh size, and far away from the cell, it can create core cell size where it is not required to understand the flow physics. Okay, so let me just quickly go through the your WhatsApp chat. Mohammad Nijam, I don't see what you have completed so far. Ajoy, okay, I don't want just your name. You also please name along with the status of your work you have completed so far. Like Aman wrote, like Aman completed geometry, mesh, and name selections. Very good, Aman. Similarly, Sayak completed geometry part, but I could not put my geometry into meshing part. So I will come to you, Sayak. Okay, we can discuss one to one, Sayak. Please don't uh, do any other chat. Only give me your feedback, status of what is the work status that you have done so far. So if that is the case, if you are all done with the meshing, now I have the task to you to explain what to do after the meshing and how to understand the physics of it. Before that, I got a question from you all, like why we are solving the partial differential equations and what is the necessary of solving this, why we creating the mesh, everything. So instead of going to the complex thing like solving for a fluid, you can also code for yourself. Here is one problem that I can show you, that coding of CFT or solving a partial differential equations for um, a problem with the boundary conditions with any method. Right now, I will show you the simplest possible method that you can understand in a better way. Uh, Mohammad Nijam completed up to meshing part. Okay, very good, Nijam. And Manju. Manju completed geometry and mesh part. Very good, Manju. Priyanshu also completed geometry mesh. And what is the question mark? Why you are having a question, Priyanshu? Others, I see there are good number of people in this WhatsApp group, around 18 people. Others, can you please text what is your status? Arhit, can you repeat your question once again? Arhit or Raman, someone asked what is our problem, why we are doing the partial differential equation, solving the partial differential equations, or what is the background for it? What is actually your question? If I
Hello,
want to recollect it once
sir.
again. Yes, Arhit.
Am
Yes.
I audible, sir?
Yes,
Sir,
you're audible,
actually, the
Arhit.
problem is like they are not getting it, sir. Why we are discretizing it and why
Hmm.
we are simulating, like to simulate the flow, why we are generating the mesh
Okay.
for mesh, and how we are partially differentiate means how we are solving the PDEs in each of the cells. How the
Okay.
computer is doing all these things, like they are having some issue in that.
Hmm.
So can you just clarify that doubt?
Fine. Right. So how many of you solved partial differential equations with the boundary conditions, or how many of you already completed your vibrations course?
Sorry, sir. Actually, vibration is not in the syllabus of these students.
Okay, so fine. So if that is not in the syllabus,
Uh,
then I can explain in a simple terms for
Sir,
your
in
understanding.
this session, the second year, third year, and the final year, the
Hmm.
all years students were present, and the second year now have completed like the heat transfer, fluid mechanics, this part.
Okay, sir.
So it is
Thank you, sir.
difficult for that, and but the other students have completed like the fluid mechanics part and the heat transfer part.
Okay, sir. Okay, sir. Thank you. Okay, sir. Ravindra Manju, sir. Okay, Manju means Ravindra Manju, sir. Sorry, sir. You have completed up to mesh part. That is fine. Okay. Pragya also completed up to mesh part. Priyanshu. Okay, name selection is your question. So others also please put your status, like what is the problem? I mean, what is up to what status you have completed the things, of what part you have completed. So right now, for your understanding, for your better understanding, I will give you a small problem. I will not give you a small problem. I will just try to teach you in a simpler way. So I have a condition like this. Suppose the condition is um, d square x by dt square equals to um, say some constant. I will say some constant k, where okay, x and t are independent. X is the spatial parameter and t is time. If x is a spatial parameter and t is time, then what actually d square x by dt square represents? Can anyone answer it? Chaudhary asking for, can you repeat for the meshing part once? Sure, Chaudhary, we will come to that. So we are having today's one session regarding the question of why we are doing a meshing and the details. So for your simple way of understanding, I'm going to teach you a very basic way of understanding this partial differential equation. So here I'm taking only one variable x and t. Sorry, only one. This is not independent parameter. Just a second. So t is an independent parameter and x is an dependent parameter. Okay. So what is meant by d square x by dt square? Can anyone tell me then?
Sir, in
Yes,
terms of
sir.
x, is x like displacement or anything?
Yes, x is the spatial coordinates. X is the position vector.
Position vector. Okay, sorry. So
X is the position vector.
So I think sir, first differential will give some velocity, or and after that sir acceleration. Is it so? Sir?
Yes. So first differentiation will give you the
Velocity, sir.
velocity. That means dx by
Dx
dt
by dt
equals
equal to
to
v.
kt
Kt, yes.
plus constant
Plus c. Yes, sir.
k2. Right?
Yes, sir.
Here we having only one one independent variable and one dependent variable. So we are using the direct ordinary differential equation instead of going to the partial differential equation. If you are having multiple variables, multiple independent and multiple dependent variables, then you may need to go for the partial differential equations. So here, let's see this only one equation, dx by dt equals to k1t plus k2. So how many of you know to solve this equation, if I give t naught equals to t naught, that means t at 0 second, say t at 0 second. At t equals to 0, x equals to 0. At t equals to 0, dx by dt equals to say 10 meters per second. Why I gave two boundary conditions? You see, I gave two boundary conditions, that is at t equals to 0, I gave x equals to 0, and at t equals to 0, I gave dx by dt equals to 10 meters per second, that this is velocity. Yes, Arhit, what is your question?
Yes, sir. No, sir, not question. Like, sir, you gave two boundary condition to solve the two constants K1 and K2 for from the
Yes.
first. Yes.
Yes, everyone please remember that here we have a second order differential equation, that is d square x by dt square. So we need how many boundary conditions?
Two boundary conditions. Sir.
Minimum two boundary conditions. And this we call, that is if you have a direct value of your parameters, that we say it as a Dirichlet boundary conditions. And this kind of parameter we say is a derivative called Neumann boundary conditions. Boundary conditions nothing but BC. Okay. So we have now two boundary conditions, dt equals to sorry, at t equals to 0 second, you have displacement x equals to position vector x equals to 0, and t equals to 0, you have dx by dt equals to 10 meters per second. Okay, so this is fine. So how further you can solve this problem? If you are doing a direct integration like this, d square x by dt square equals to k1, then you will get the solution of this problem in such a way. So what are the other ways to do this problem? Can we do it numerically? Because it is a very simple problem and you can do the integration, direct integration, and you can solve this problem like the same way that we did here, like for the velocity. And if you further integrate, what will come? K1 t square plus K2 t plus K3. And if you have the boundary conditions, you can apply and you can solve for the any t, right? So other way of solving this problem is discretizing the condition in such a way that uh, you need to create the domain. All right, you need to create the domain. Suppose instead of considering the t as a better way, I can say this point, this point, this point, this point, this. This is my time t. Okay, so and say this is my displacement x. So at x equals to at time t equals to 0, x equals to 0. So I can just give a dot here. Suppose at time t equals to 1 second, if I got x equals to some x1, I will put it like this. In the similar way, if you have a constant acceleration means you will get a curvature like this. It won't come like this. It will come like a parabolic curve because you have a d square t by dx square. It is a constant acceleration. So along with time, you will get a parabolic kind of x displacement. That means what I'm trying to convey here is you no need to solve in the same way that every time that you're performing in a direct integration. That means direct integration, how you can solve this d square t by dt square is equals to k1. If you're solving with a direct integration, what will happen? You will, the second step, you will get this one. And the third step, you will get x equals to k1 t square by 2 plus k2 t plus k3. So this is how you will solve. Now it is a simple algebraic equation. If you put what is your t value, t we have t equals to 0, we have x equals to 0 and t equals to 0, dx by dt equals to 10 meters per second. If you put these two values, you will get the equations of k1, k2 and k3. Okay, so that we're using this algebraic form, you can directly plot this x and y, x and t plots. That is at t equals to this, I will get x equals to this one, and the t equals to say 10 seconds, whatever the t value I give for you, you can easily obtain that. All right. Sorry. Another way to solve this equation is by discretizing it properly. So how you can discretize it? Suppose take this second form. The second form is, can I drop it down? The second form is dx by dt. How many of you know the Taylor series expansion? How many of you know the Taylor series expansion? Yes, sir. What do you know about the Taylor series expansion?
So Taylor series expansion, actually we use it in case of to derive the Euler's equation or Bernoulli's equation. In that case, sir, we are using Taylor series equation, like we are expanding the term to find out. Sir, I'm not clear about that. I need to revise it once, but I have learned it.
Fine. So I will take this Taylor series expansion. I will not go to the Taylor series expansion, as I'm not going to derive that or the things, but I will give you the idea of how another way we can solve it. So suppose dx by dt you have, it is the time, and you have the x1 equals to, this is your x1 at time t equals to 0, and this is your x2 at time, it is time t naught t1. Suppose this is x3, and suppose this is x4. How I can write this dx by dt numerically? Dx by dt, you can write it numerically like this. That is, any part, at any part, if you want to see, I can say x2 minus x1 by t1 minus t naught. Can I write like this?
Yes, sir.
Okay. So now you just did integration way. Now I also say I can do in this way. That is y I, sorry, I should not go to y I. Let me just erase this. So if I want at x2 equals to x1 plus delta x, right? Or I can say dx, because let's assume we are considering a very small part, very small part. So x2 equals to, that means I want to find out the value of x2 that is correspond. Sorry, this is not. Let me use the same terminology. x0, x1, x2, x3, right? Please follow the content. I am doing some mistakes here. If you're following the content, you can also raise your queries that it is not t2 minus t1, because I used x2 minus x1 on the top and I used t1 minus t0. That is not correct, right? So it should be t2 minus t1, x2 minus x1 by t2 minus t1. So now I want to find out the value, this one x2. If I want to find out that value x2 from the Taylor series, I can write in such a way that x2 equals to x1 plus dx by dt plus into delta t, okay, plus d square x by dt square plus, sorry, delta t square plus d square, and so on in the higher order terms. Let's not go to the very higher order terms, but how many of you now recall this Taylor series expansion? Can you tell me that? How many of you just recall this? There will be a factorial also.
Yes,
I am
sir.
not able. Yeah, the factorial also you can write it. You write the correct expansion. How many of you recall this Taylor series expansion now? X2 equals to x1 plus dx by dt delta t plus 1 by 2 something some factorial d square t by dx square. Right? Only Pragya, Abhishek. How many of you recall this Taylor series expansion now? You can go through the correct expansion form. I'm not clear with the correct expansion form right now, but I have the idea of it, as you are asking for the instant form. If you're going through the correct expansion, we will get the correct equations, but still the idea is same. If you are having this Taylor series expansion, okay, you will get x2 equals to x1 plus dx by dt into delta t plus higher order terms, whatever the higher order terms, and we can round it off up, as per the requirement. So in such a way, now I can find out the x2 by using this particular Taylor series expansion. That is x2 equals to, I have the information of x1 based upon my previous time series. Let's say you already have information of x1. So now I'm finding to information of x2. So dx by dt, I can write it as x2 minus x1 plus t2 minus t1. So or you can use the, I can also use this one, right? No, this is the correct one. x2 minus x1 by t2 minus t1 into delta t. Say consider your delta t equals to 0.5 seconds. And you have time information t1, you have time information t2, x1 information, only you have the unknown is x2. So segregate the unknown here from these two equations, that is x2, and solve for the x2 as a function of x1 comma t1 comma t2 and the delta t, whatever the delta t. So this is also the numerical way. This is also called as a numerical way that you can solve the any ordinary differentiation or the partial differential form of equations, right? So now did you get the idea? That means in this form, what you need to do is first you need to divide your domain. Like divide your domain means if you are having a time from t equals to 0 to t equals to 10 seconds. This is only the time domain. I did not consider any spatial domain, other independent parameters also will be there. This is one dimensional and also only time domain. So from t equals to 0 to t equals to 10 seconds, I want to find out the displacement based upon the function that given here, that is d square x by dt square equals to k1. Based upon this this ordinary differential equation, I want to find out the x. If you plot it by doing an analytical solution, you will easily get this kind of plot, a parabolic kind of plot, because its acceleration is a constant one. So analytically you can obtain it very easily, and at any time t instant you can obtain it. But I don't want to do it analytically, I want to do it numerically. Because this is a simple ordinary differential equation, you can do it analytically, or also you can do it numerically. So if you want to do it numerically, what you need to do is you need to divide your independent variable. What is your independent variable? My independent variable is time. So I divided my time in such a way that between time t equals to 0 seconds to time t equals to 10 seconds, and I divided this for every t equals to 0.5 seconds. Got it? And I use the Taylor series and identified the what is the x1, x2, x3 at every time instant in such a way that at a gap of 0.5 seconds. What if you decrease the or increase the time delta t, this independent variable? This independent variable, if you increase, you will get similar solution but much more accurate. If you further decrease, you will get much more accuracy. But the number of points, if you decrease the delta t between 0 to 10 seconds, and you keep on decreasing the delta t, the number of these points will increase, right? So, but you will get a much more accurate solution based upon this Taylor series. I hope now this is clear. So in the same way, whatever the time we are dividing here, like the same stepping here, we are dividing the cell size. The cell sizes are also acting like this. If you are dividing cell size very, very smaller, you will get much more accurate solution. If you are using a coarser one, like between the types of cells to very large number or very large stepping, like from this particular to only one or two cells, then you will get very bad solution or maybe improper solution also. Okay. So now did you get the idea of why we are doing this domain, why we are splitting it? These equations you see these equations, these are ordinary partial differential, ordinary differential equations. It is easier to solve analytically. So no one taught us why we are doing in this way, why not to doing the numerical way. But there are no direct solutions for the large partial differential equations like the Navier-Stokes equations, what you are seeing. For the complex problems, there are no direct analytical solutions. It is very difficult to solve like the way we solved with this ordinary differential equation as analytical way. So the only availability is to solve numerically. That means this particular division method. We have to divide our domain. Here the domain is a time domain, and there we have domain is a spatial domain, and time is also a domain that I will show you again how the time is also a domain. So first is our spatial domain. In such a way, we have to divide the domain into segregate the parts. Then only we can progress our solution from the boundary condition. This is the boundary condition. So they gave the details of the boundary conditions that at t equals to 0, I have x equal to 0, and dx by dt equals to 10 meters per second. So I have the boundary conditions here, these two things. So using those two only, I should first find the x1 value, then only I can find the x2 value, then only I can find the x3 value, then only I can go for the x4 value. So like that, you have to march forward in time as you already described your domain, then only you can find this x1, x2, x3, x4. Without these boundary conditions, like if I did not give any boundary conditions or improper boundary conditions I gave, then you cannot march the solution forward. I mean, you cannot get the correct solution, or you may not able to solve the equations also. So now this is the concept behind why we are creating the domain and why we are splitting the into small cells, and the importance of mesh size. What is the important? Why we are solving the partial differential equations for understanding the solution. Partial differential equations are derived based upon the laws. What are those laws? Mass conservation, energy conservation, and momentum conservation. Those are the governing equations. So governing equations are in the partial differential form. To solve the governing equations, we don't have any analytical way like the simply that we solved using the analytical ways, the simple approach that we did the integration. We only have the approach to solve them numerically. So that we need to divide the domain, spatial domain and the time domain into small parts. Then only you can identify the solution at every time instant and every spatial location. So now, how many of you got the idea, clear idea, at least the some idea of why we are solving this particular partial differential equations to get the solution in the flow domain? Can you please quickly raise your hand, or if you have any doubts, you can let me know. One,
Sir, I have
two,
one doubt.
three. Yes, sir.
Regarding, so it's a general doubt like regarding the coordinate system we are using while discretization. Sir, if we are solving the Navier-Stokes equations, sir, is it like we are solving it in the Cartesian coordinates or cylindrical coordinates or spherical coordinates? Because sir, like there are three types of coordinate systems. So, sir, if we are solving it, how we can determine which coordinate system we will be taking?
We can take any coordinate type of system, but the general way is taking the Cartesian coordinate system as its simplicity and Cartesian coordinate system. Some problem specific, like if you are simulating a flow over Earth, flow on Earth, like how the cyclones are happening, how the torpedoes are creating. So if you want to simulate those kind of things, it is better to go for the spherical kind of coordinates because the object is in the spherical way. So it depends on the problem specific. To simplify the problem, the user generally takes, most of the users takes the Cartesian coordinates, but you can also take cylindrical coordinates. That depends on how you are programming it. I can show you the Cartesian coordinate and spherical coordinates way also.
Okay, sir.
Just give me some time. Somewhere here. Okay. So once again, how many of you got the idea of this solving the differential equations with the numerical schemes? Just raise your hand. I did not see clearly. How many of you understood the concept, the one I just taught you? Please raise your hand if you understood the concept, or you can text on WhatsApp also if you understood. You can text on WhatsApp that your name and you understood that. Can you all please quickly do it? 3, 4. Ajay, do you have any queries, or you did not, or you are failed to understood something? Okay, 5, 6. 5, only 5, 6. Yeah, this is the simple velocity acceleration problem. I did not take any complex problem for your better understanding. So yes, this is a simple velocity problem. You might have understood by this time better. So if you are still having a doubts, or if you are not able to capture these things, I suggest you take some basics of solving these partial differential or ordinary differential equations, the methods of solving ordinary differential equations. Yeah, that's great. So please down your hands. Let's go to the next concept. And one more for your some further better understanding. This is a two-dimensional, and also the space is also included here. I hope you all can see this particular problem. So here the problem is, how many of you are good at understanding the IC engines and how heat transfer through fins is occurring. Like how we are cooling it, right? Through fins. For a bike engines, through fins we are exchanging the heat of IC engine to the atmosphere. Is that concept is clear for you all?
Yes, sir.
For all, Arhit, just let me see for the others also. If it is problematic for you to raise your hand or answering in the meet, you can also use the WhatsApp for your convenience, your convenience. Yeah, okay. I believe that is comfort for you. Like this concept is very comfortable for you. So here, the problem is they're stating the problem is it's a two-dimensional problem. Let's not worry about why I'm going into the heat conduction again. So it is just for your understanding of CFD. CFD includes solving a problems with a numerical way. So it cannot no need to be only fluid. It can also be a heat conduction problem with heat conduction with the fluids also. Okay. So heat conduction with fluids also. So here I have a, plate here, some metal plate, and that metal plate is insulated with some material, any material that we have, and insulated. And here I have a temperature giving as a function of so some function. So my metal plate is one particular edge of the metal plate is supposed to exposed with some heat source. That heat source is varying in such a way that as a sine function. As a sine function, my heat is increasing and decreasing and increasing and decreasing with the mean of 100 sine pi x, like this. Increasing and decreasing in the sense here it is more temperature maybe, and it is less temperature, and more temperature and less temperature. Like this, it is varying from left hand to right hand. And other all three are insulated. So here the question they asked is, if this is the temperature case, and how the temperature distribution in the entire slab, entire metal plate. That means here you're increasing the temperature and decreasing the temperature. It need not to be uniform temperature everywhere, right? Maybe at this point, whoever, maybe Arhit is standing at this point, standing on this plate at this point, he may feel safe that this is the coolest point on this plate, so he gets a less heat. Or if he is thinking that here it is a less temperature point, so if standing here may gives the less heat for him, or the less temperature that he can feel. So okay, so that's way the temperature distribution is happening. So how to find out that? It is a two-dimensional problem, and it's not easy to solve analytically also. So first we need to go to what are the conditions, what are the governing equations solving this problem. So the governing equations, again, these equations, I don't want to give you the details of or dig into the details of what are these governing equations. So let's assume the temperature is being governing by uh, dou square t by dou x square and dou square t by dou y square, where x and y is the spatial coordinates. This is your x and this is your y. Okay, so x and y are your spatial coordinates, and this is the temperature that you are exposing. Can anyone guess how the temperature distribution in this plate? Can anyone guess and tell me your answer in either WhatsApp or unmute yourself? Can anyone guess how the temperature distribution looks like? Quick quiz of anyone. Okay, so let's dig into the problem. As I said in the same way earlier, you have to discretize your domain. This time the domain is x and y, both x and y here. You have to discretize in both x and y directions. Yes, Aman. Aman, or who is that?
Yes, sir.
Any queries, Aman?
I don't know, sir. I don't know.
Okay, okay. So in the same way that earlier we have discretized the time domain as number of sequence, number of small components. Now I have a domain in such a way that x and y. My x is varying from along this particular location 1 to location 2, and in the same way y is also varying from this location 1 to location 2. So now I am discretizing those things. Like you can see the points. I use the points, not the edges, like boxes. So this is one box for me, and this is one box for me. Like that, I discretize the parts. small parts to identify the um, mesh boxes. Like, okay, to identify the mesh boxes, I discretize um, spatial domain. This is a spatial domain. I discretize the spatial domain. Okay. So how after solving the equations, now you can see these are the partial differential equations, dou square t by dou x square. I gave you the partial differential d square x by dt square. So here the partial differential equation is two-dimensional, and I got in such a way that dou square t by dou x square. And to solve the equations, I first converted them into this particular form that you can see as the Taylor series expansion. So after converting them into the Taylor series expansion, I solved it algebraically. So let's skip all those algebraic formulations and everything, as those are not the theme for. So once you solve that, you will get the temperature distribution like this. You see there is a 100-degree temperature at this maximum is here, 100 degrees Celsius, and the minimum is 0 here, as it is a sine function. So it is starting as 0 and it is going up high and it is coming to 0 again, like this. So my temperature distribution is like this: 0 at both the ends and very high temperature at the middle. So this is how the temperature distribution looks like. So entire plate, the minimum temperature is around 60, because you see the entire distribution is around 60 degrees Celsius, because it is occupied with more or less a light green color. So this green color saying that what is the color bar indicating 60 degrees Celsius. So even though you are heating the slab with maintaining the constant temperature at one end and insulated at all other ends, and the maximum temperature in the slab is 100 degrees Celsius, you will see the temperature, the final temperature in the entire slab is only 60 degrees at the all other portions. Okay. So it does not necessary that you will get continuously heated up to all the parts up to completely become 100, because you also have here it is a heat source, and you also have a heat sink here, because it is maintaining 0 degrees Celsius here at the both corners because of the boundary conditions we gave. Clearly try to understand this. You are heating with 100 degrees Celsius here. That doesn't necessarily means your entire plate should become 100 degrees Celsius, because you also have a heat sinks here, 0 degrees Celsius. That means based upon these two heat sinks and heat source here, you will get a steady state temperature in the final entire metal plate at 60 degrees Celsius approximately in the remaining zone, and 100 degrees here and 0 degrees here. This is how the distribution looks like. And one more problem is the same way you are solving, and additionally at one end, let me go to the problem. Additionally at one end, you remove the insulation. This part you remove the insulation and you added a heat convection. A convection due to the air. Air is passing by touching this metal plate side surface. If it is passing at some particular velocity, saying that some non-dimensional heat convection coefficient is this much, that means it is taking heat. Just assume that it is taking heat. So how then how the temperature looks like? Okay, this is how the temperature then looks like. You see the temperature is much lesser. It is much lesser than 60, or it may be around 40. I can say this is around 50. I can say this is around 60, and this is 100, and this is 0 degrees Celsius, and this is 0 degrees Celsius. If you're trying to solve this kind of problem using analytical solution, it is not possible, because analytically solving those things equations is not possible, as it is involves complex boundary conditions. So you definitely need to go for the numerical solutions. Got it? So now everyone get the clear idea why we are doing these things of flow over a cylinder using the mesh or anything. If yes, you can just raise your hand, or you can text in WhatsApp, or you can text your queries in the WhatsApp also, anything. I believe I gave I put my efforts in help you to understand why we are doing this meshing, discretizing the domains, what is the reason behind it. If you understood or if you get the subject clearly, just raise your hand. Then we can forward to the next concept. Please raise your hand if you got the concept. Okay, Arhit. Arhit, I just want you to drop your hand all the time. Yes, you already learned many things from here, so I just want to interact others. If you have any queries, you can ask me personally. Let me interact with others. Arhit has learned many things here, like he used to ask at least per day minimum 100 to 200 doubts. It's like you can understand very difficult for me to answer all his questions every day as he is an enthusiastic person. So I believe you all also in the similar fashion, like very good in understanding the concepts and you can clarify your doubts. So let me know if you have any queries. Ajoy, are you there?
Yes, sir. No query.
No queries. Did you get the concept?
Yes, sir.
I believe you understood the concept. Let's go to the main concept right now. So many of you already performed the meshing part, right? So I will teach you the meshing part once again for your clear understanding as I taught you. Who told you who wants the meshing part? Does to repeat the meshing part once again? Chowdhury. So Chowdhury is a faculty or a student here? Hello.
Sir, he's a student, sir.
Okay, Chowdhury. So can you recollect it from the video? Like I already uploaded the video in YouTube yesterday. I hope you followed the video what I presented yesterday. So if you still have any doubts from that, you can just quickly ask now. What is the problem that you are facing in the meshing part? Chaudhary, are you there?
Yes, sir.
Yes, Chaudhary. Can you tell me what is the problem that you are facing in the meshing?
Sir, in boundary conditions.
Boundary conditions. So boundary conditions, we will go once again. Anyone knows how to erase the all at once? Okay, let me take a new sheet. So Chaudhary, um, everyone, let's focus now on the boundary conditions. Why we are giving the boundary conditions and what are their importance? Boundary conditions we just understood what are their importance. If you don't have boundary conditions, you cannot solve the problem, even though if you have a boundary governing equations. So in the similar way, let's go to the aeroplane again. So this is my aeroplane. It's flying at some high altitude, 10,000 kilometers, some very high altitude, 1,000 kilometers or something. So at that high altitude, if it is flying, say you have a requirement that you need to study only the flow over the aeroplane. You want to see only the flow over the aeroplane, not the how the aeroplane is moving. So as a fixed frame of reference, you are sitting on the aeroplane. Let's say you are sitting on the aeroplane, not inside also, on the aeroplane. And with your reference, what will happen? What is actually happening is you won't see that you are moving in the space. You feel like air is coming at a speed of the same opposite velocity. If the aeroplane is flying at a velocity of say 1000 kmph and you are standing here, say Arhit is standing here and trying to see what happening in the atmosphere. Arhit say he is standing here and the aeroplane is flying. So now he won't see that he cannot feel like that he is moving at a speed of 1000 kmph. The air is coming at a speed of, he feels like the air is coming at a speed of 1000 kmph, as because it is his frame of reference. Okay, so now we are going to simulate the same. We are going to simulate in such a way that as I want only the flow over the aeroplane, I don't want the complete other details, what will happen, what is happening either when aeroplane is passing or from the, not from the stationary frame of reference. I want to see how the flow is looking like when we are standing on the aeroplane, and flow distribution on the aeroplane. So what we need to do is, we need to do first create the geometry of the aeroplane, and then we need to create the domain, the computational domain. That means the space where your flow is moving. Got it? So this is the computational domain that is enclosing your geometry. And in this computational domain, uh, बाद में आएगा थोड़ा class. Just a minute, guys. Okay, sorry for the interruption. So now I created the computational domain like this. Okay, so in this computational domain, let me hatch in such a way that, as you already did in your engineering drawing, suppose I will hatch this aeroplane as a material. Okay, so how my flow should react? I don't want the flow to enter into the aeroplane, right? My flow should not enter into the aeroplane. My flow should come here, and it should travel along the aeroplane surface, and it should touch Arhit, and it should leave like this, right? It should not enter into the aeroplane. Since as a person, you can know that flow should not enter, as a physical reasoning, flow should not enter into the aeroplane, because you are a human, you can sense that it is an object, so flow cannot pass through the object if it is a complete solid object, fully solid object. So because software cannot know, right? Software cannot know what is this, what is the aeroplane, whether it is an object or not, something else. So you have to give the condition, some condition to the software, saying that this outer region, let me draw this outer region once again, saying that this outer region, whatever this outer region is, as a wall condition. You should say that this as a wall. Wall means what will happen on the wall. The flow cannot enter through the wall, right? So how many of you understood this concept? Just raise your hand quickly. Let's not spend too much time on this. How many of you understood this? Okay, only one, two. Please be quick. Only one, two. Or you can also respond in WhatsApp. Yeah, fine. So this condition, very good. So this condition we applied now. Okay. And also we have a computational domain here. This computational domain also won't move. This aeroplane also won't move. What is moving? Only the flow is moving. From where? Flow is moving from the left side. That is particular this point. Let me take some other color. Flow is moving from this particular point. And exiting from here. Okay, this is your inlet. We say this is as a inlet, and we say this as a outlet. Got it? Okay, here I need to give, because I already now applied to the flow, to the software, saying that this is my wall boundary, so I don't allow the fluid through the boundary. But what about these remaining edges? There are still remaining edges. So what conditions should I give this all four edges the computational domain? Manju sir, you have any doubt? Okay. So
Not
what are the
audible.
okay, thank you. So what are the conditions I should give? What are the boundary conditions for these four remaining edges? Let's see one by one. So first, our first condition, what we know is the flow should come at a speed of the same speed what Arhit is feeling on by standing on this aeroplane. Because now we are dealing with the frame of reference, saying that in the frame of reference of Arhit, saying that that aeroplane is constant and the flow is coming related to the same velocity what aeroplane is flying. So the air flow is coming with the velocity of inlet velocity equals to 1,000 km/h. If you can convert into meters per second, you can also do that. So this is my condition. I gave it here. All right. What are the other parameters I have in my governing equation? If you see the Navier-Stokes equation, we have not only the velocity, we also have, let me show you the parameters so that you can understand. We have the velocity parameter V, pressure equals to P, density equals to rho, temperature equals to T. Okay. And also if you give the time as an steady case, you can also give the time. Time is also one parameter. So if you consider steady, it will be a steady state condition. So these are the four parameters: velocity, pressure, density, and time. So you can ask me now, sir, you are giving only the velocity as a velocity condition. What about this pressure, density, and temperature? These are also unknowns, right? You should also give the boundary conditions. These are also involved in the partial differential equations of Navier-Stokes equations. So you are also giving these conditions. Fluent does not show you that, but it also automatically give you these conditions in the background. Like if you are giving air as a fluid, then it also automatically takes rho equals to, at the rho inlet air equals to 1.225. Suppose if you're flying at high altitude, the density decreases, but let's assume this density is same, kg per meter cube. And it also gives the boundary condition pressure equals to P atmosphere. Okay, and temperature T equals to T atmosphere. Okay, if you assume that temperature has no effects, temperature has significantly less effects, you can maintain the temperature as constant in the entire computational domain. Also, if you are seeing that density is also not significantly changing, you can assume the density also constant in the entire computational domain. Okay, so now the key boundary conditions are velocity, pressure. So both you applied here because you know this is the atmosphere. So the atmosphere pressure you applied as a boundary condition, and the velocity also you applied as a 1,000 kmph. So now this boundary condition is done. What about the outlet? At the outlet, you don't know the velocity. What is the velocity that actually Arhit is seeing at this outlet boundary condition? If it is very far, because why we are not able to sense the guess the outlet boundary condition is, if you see the wake of the aeroplane, it is creating a disturbances in the wake like this. You see these wakes, it creates a disturbances in this atmosphere. So it does not necessarily to have the same velocity at this exit also with the same velocity that you are giving at the inlet, right? How many of you agree with this statement? This aeroplane is the object, is disturbing this flow. So I'm saying that this exit boundary also does not necessary to have the same velocity that you are giving at the inlet. So how many of you agree with this statement? Did you get my question? The question is, I'm saying that the exit velocity need not to be 1,000 kmph. It may be more or less than that. I'm saying that V exit is not necessarily equals to 1,000 kmph. So what should be the condition? What else I can use that condition? This is not the exit velocity that you cannot use as the exit boundary condition. So what else I need to use? I cannot use exit velocity as 1,000 kmph.
Less than 1,000 kmph, sir, because it can produce some difference.
Sorry?
Difference. So less than 1,000 kmph, sir.
Less than
So
1,000
it can
kmph.
produce pressure.
So
less
it can
than
produce
1000
pressure
kmph,
difference.
yes, but we
So
don't
it
know
can
the value,
produce
right?
pressure difference.
It can produce pressure difference also, but we don't know the value. How can we simulate that if you don't know the value of your, you cannot give the boundary condition also. If you are not knowing the boundary, these boundary condition, how can you give the boundary condition to solve this problem? You don't know the velocity. Velocity definitely you know, because of these disturbances, it creating the disturbances at the exit. So velocity at the exit need not necessarily be 1000 kmph. So what else then? Say we are already assuming that rho is not changing, that is density is not changing, 1.225 kg per meter cube. So this is constant. Temperature is also constant. We are assuming that temperature, so temperature is not constant. So what about this pressure? Pressure at pressure at exit, not atmosphere. What about this pressure at exit and velocity at exit? These two things are not necessarily to be the same that what already we mentioned at the beginning. So that's why what fluid dynamics usually do, the fluid has a good behavior that if your object is very small, like this, let me draw it very clear. If your object is very, very small like this, and your computational domain is such a way that see, compared to my computational domain, my object is very, very small, is it? Compared to my, this is my computational domain. See, this is the object, circle is the object, and this is my computational domain. So compared to the computational domain, my object is very, very small in this. Pragya, you have any doubt? Okay. So in this condition, fluid has a property that it diffuses whatever the velocities, because you have a more free stream velocity here. So this velocity, even though it creates a small disturbances here, very small disturbances it can create. So these disturbances will nullify and it becomes the same velocity after some period of time that what you have in the inlet. But still, it is not correct to use it as the same velocity at the exit, that we apply the V inlet, that you cannot apply the same velocity at the V exit, because that is not the appropriate boundary condition, since the both will become a Dirichlet boundary conditions. You may need to recall what are the digital boundary conditions, but one more better option is to use the, as I said, the velocity now becomes the same velocity at this exit. People generally use the velocity boundary condition at the exit as a Neumann boundary condition, that is dv by dy equals to 0, or dv by dx, not dy. That is the first order derivative. That means the change in velocity along this boundary is 0. There won't be any change in velocity along this boundary is 0. They are not mentioning it should be specifically v exit equals to, they are not mentioning that v exit equals to 1000. They are mentioning that the change in velocity at the exit should be equals to 0. That is the case in the atmosphere. If you see, if you are creating any small disturbances at some point in a big pond, okay, a big pond is there, a big pond or a river, something, if you are creating a small disturbances, by the time the disturbance, this is the disturbance, suppose you are creating, by the time the disturbance reaching to the extreme ends of the pond, the disturbance itself nullifies, or it lost, it cannot sustain for that long, right? If it is very big pond, have you anyone observed that? You may have observed many times by throwing stones in the study pond. If you are throwing stones in the study pond without not disturbed pond, you will see the waves will pass in the water, but finally it got nullified or dispersed very quickly, and by the time it reaching their boundary, it won't sense the much difference. Is this phenomena is reasonable to you all? Yeah. If this phenomena is reasonable to you, you won't see any disturbance. such that represents the condition of dv by dx equals to, that is the first derivative of the velocity, equals to 0. And at the exit, you can say in the atmosphere, based upon our physical experience or the experimental experience, the atmosphere very far also, that the pressure is also equals to, again, P atmosphere. Got it? Fine. Yes, Abhishek, any queries?
No, sir.
Yeah. And one more thing I need to mention here, if you are applying one parameter as a Dirichlet boundary condition, people generally also, you can apply, no need to be P atmosphere equals to this one. You can also take another boundary condition as dP by dx. The same way here you are taking dV by dx as equals to 0. In the inlet also you can take dP by dx equals to 0. That means no change in pressure as you move along the x. If you move along the x, there won't be any change in pressure until you reach the this particular aeroplane. Until just before you reaching the aeroplane, you won't see any change in pressure. After reaching the aeroplane, on the surface of the aeroplane, you will see the change in pressure that governs by your governing equation. Governing equation do those modifications. Got it? Yeah. So this is all the reason behind what we are doing in this computational domain and creating the object, and why we are creating that big surroundings around the circle. What is the necessity of creating that big space instead of creating a small space? Why we are creating that big space? And also you have a question that, sir, you have given an inlet at this particular boundary also, here also, and here also. How many of you are having this question that I having the inlet at this horizontal lines also? How many of you are having the question? I'm giving the velocity inlet boundary condition. The conditions we are applying like this: velocity inlet for this one, 1, 2, 3. For 1, 2, 3, we are applying the velocity inlet, and here we are applying the pressure outlet, and here we are having a valve. Now the question is, how many of you have the question that why you are applying the velocity inlet at 1 and 3 boundary conditions also? How many of you have that? Can you please text me in WhatsApp, or you can raise your hand here? Okay, only 1 or 2 having that question. So this condition, what I'm applying is, yeah, Priyanshu also has a question. So at 1 and 3 boundary condition, sorry, at 1 and 3, if you clearly see the boundary condition, which will come application of the boundary condition, actually application of the boundary condition in the later section in the ANSYS Fluent, you will see that I apply the boundary condition only in the x direction. That means though I selected the edge 1, 2, 3, I give a boundary condition in such a way that only velocity in the x direction equals to some finite value, but velocity in the y direction equals to 0. That means even if you are giving a velocity boundary condition at this point, you will have the only x velocity direction along this, but there won't be any vy velocity in the upward direction. Got it? So this can help you to give the boundary conditions for these two upper and lower kind of wedges also. Because I don't want inlet, that means flow should enter through these lines also. I should not allow the flow to enter these lines. That is not reasonable for me. That is not the physical one. So the physical one is I can still allow the fluid to pass along the tangential to this boundary condition. That means only in the x direction. Only in the x direction it can move. So that is a vx velocity. So that is the boundary condition I'm going to apply in the next Fluent module. Okay, is that
Sir,
clear for everyone?
it depends on the one-dimensional flow or the two-dimensional flow. Like for the two-dimensional flow, we need to apply the velocity in the horizontal axis also.
You no need to apply the velocity in the horizontal direction also. So, but another boundary condition that can satisfy this problem is, many boundary conditions can satisfy. You can also satisfy this boundary condition by using the symmetry boundary condition that we generally say dv by dy equals to constant. That means whatever the parameter that is crossing this boundary condition, that is no change in the property across this boundary condition. Is that your question, sir, or something I missed it?
That means the velocity gradient will 0 for the horizontal.
Velocity gradient, yes. There you can also we say generally there's a symmetric boundary condition. So that symmetric boundary condition also we can apply on these both horizontal edges. But generally for teaching purpose or tutorial purpose, people apply that as an inlet velocity inlet boundary condition, as a simple boundary condition for that. Instead of again applying the symmetry boundary condition, we generally also give it as velocity inlet, these three, and this is the velocity exit. Okay, so now I hope this concept is clear for everyone. If still having any queries, you can just raise your hand and we can proceed for the next session. Very important one. So I thought to teach ANSYS Fluent today. It is now very important one to teach before the ANSYS Fluent, before starting with the ANSYS Fluent. Any more queries? Abhishek, you have any query? Abhishek, Ajoy, Aman, Dharmaraj, Mohammed, Mohit, Pragya, Priyanshu, Vinod, any queries? If no queries, you can type in WhatsApp, no queries, sir, and then we can move to the next concept. At least type in the WhatsApp so that I can understand that you are all following. Arhit is saying no queries, sir. Okay.
Sir, there is no query. We can go ahead.
Okay, thank you, sir. Thank you, sir. Pragya also saying that no queries, sir. So, fine. Let's go to the next important concept. So, I discussed yesterday about the Reynolds number. How many of you looked at the concept of Reynolds number? If not, also that is fine. But if anyone already seen just recollected what is the Reynolds number, you can just tell me that in this session. What is the idea of Reynolds number and what is the importance of it?
Sir, from the Reynolds number, we can identify the flow properties, that the flow is the laminar to turbulence, and also we can get the information of the vortex flow.
Yes, sir. So these kind of things, yes, sir. Also,
but sir, in the last pictures that you have shared in the last class, that means in the studies class, in this we found that there we have a Reynolds number 180. So the vortex flow, sir, is a concept of the turbulent flow. But sir, there the Reynolds number was the 180. So sir, how is the possible at the 180 Reynolds number that
vortices
I
is
do not have any
necessarily
idea
to
that according
Yes,
to sir, my opinion that the flow of the vortex flow is the concept of the turbulence flow. So maybe the value of Reynolds may be the greater than to 4,000.
Okay, sir. I will help you with that. So,
Yes, sir.
vortex flow need not necessary to be a turbulence. Vortices we can also find in the laminar zone also. So,
Okay.
so there we are seeing as external flow. So many of we know Reynolds number is quite famous for the internal flows, flow through a pipe. Suppose if we have a flow through pipe like this. So in this flow through pipe, you have a flow region starting from this particular location. Say, assume this is our starting location. And after some time, we will see the flow become developing region, like it will start like this. And you might have, many of you have seen this particular diagram, that developed region, fully
Yes, sir.
developed
Shear
region
force
and developing
distributions
region.
and
Yes, sir.
yes, sir.
Right. Yes, sir. So in this kind of particular scenario, if your Reynolds number is like generally people say in the range of 2000, if it is below 2000, this is called a laminar zone. And if it is above 2000, or there will be a transition, everything turbulent. So in this between zone also we see the transition turbulent. But I don't want to go and disturb your idea of this laminar and turbulent zone, but there are some researchers even saying that even the 10,000 Reynolds number also can be a laminar. The possibilities are there, and let's not dig into those kind of details. And here, let's assume the same default laws or default learning what we know on so far. So 2000 Reynolds number, the flow is laminar, and after 2000 Reynolds number, the flow is turbulent. So what is this Reynolds number and how we are defining this as a laminar and turbulent? If Re is equals to ratio of inertial forces over the viscous forces. So suppose how to understand this ratio of viscous forces to inertial forces. Let me tell you in a simple way. Suppose Arhit just woke up after just get up from the bed sunlight. He just woke up after a long sleep. So he has so much of inertial forces, so much of inertia. Sorry, not inertia, viscous forces. I can say it's a viscous forces. That means he cannot do such a way that any work in a rapid manner. Anything that he is going to do just after just waking up from the bed, he does in a very lazy way, right? For some time until he gets fresh up. Like he moves in such a way that every task will be slow. So that particular period, your inertia is not helping you, or your momentum is not helping you. You are dominating by some particular force. That is, we can say everything we are doing very slowly. So that region, whatever the region, that region we are saying that we are dominant by some viscous forces. Okay. So now let's assume he is playing some football or something else. There he is running with high speed, some particular speed, and he is trying to catch up the ball or trying to do something. There he is dominated by the inertial forces. He needs to do every action very quickly. So now you see the differences. At the early morning, he just woke up from the bed and he is dominated by some viscous forces. Viscous forces means he is doing everything slowly. So in the same way, fluid also has dominated by the viscous forces. If it is dominated by viscous forces, it goes in a layer by layer form. That means like this. The middle layer has a high velocity and the remaining layers has a less velocity, and its velocity distribution like this. So one layer by layer on top of one, top of one, top of one. So these kind of things are dominated by the viscous forces. If it is dominated by the viscous forces and flow is in the layer by layer form and it moves very, very smoothly, flow moves in very, very smooth manner and in a lazy way. Okay, because it is dominated by the viscous forces. If it is dominated by the inertial forces, the fluid, you cannot expect how it is going. It goes in a random way and it becomes very turbulent, such that uh, all the layers except near to the walls, all the layers, like, let me draw it once again. Except near to the wall, all the layers has a very high velocity, almost approximately equal to the same velocity, and much more chaos in nature. If you see the eddies, it will be turbulent, like it many things having the same particles and they are very turbulent. That means their action and their velocity, the fluctuations are very random. That means their movements fluctuations are like if you see any boiled I can say molecules. They are molecules or atoms. They are moving with it very randomly at high speed, right? Exchanging their momentum with other particles with high speed. Here, the exchanging of momentum is not possible in such a way that we are seeing here. So this is what dominated by the inertial forces. If your viscous forces are less, you are getting dominated by the inertial forces, then you will see this kind of phenomenon. This is why we are differentiating between inertial forces and viscous forces. This happens everywhere, not necessarily to be internal flow or not necessarily to be external flow. It happens everywhere if there is a flow and there is an object. Okay. How many of you now understood what is this ratio, what is this inertial forces, and what are these viscous forces? Just in a random, generalized way, not like a detailed mechanics way. How many of you understood this now? You just can raise your hand. Only one or two, three, four. Okay. So if you are not still clear with, you want to get more details of this Reynolds number, we can discuss it one by one. But as we are running out of time, let me complete this concept today. So this is the Reynolds number. Sorry. So here with this Reynolds number, based upon the inertial forces and viscous forces, if you know the dimensional analysis, then you will end up with, you can look into what is the dimensional analysis, and then finally you will end up with the Reynolds number is a formulation of rho V D by mu, or rho V L. L is the characteristic length by mu, where mu is the viscosity of the fluid, dynamic viscosity, specifically dynamic viscosity, and rho is the density of the fluid, v is the velocity, d is the diameter of the cylinder. If you're using some other object, any other object other than the cylinder, you can find out its characteristic length. Characteristic length in the sense, if you're taking a cylinder, its diameter is the characteristic length. If you're taking a flat plate, its length of the plate is the characteristic length. If you're, so depends on that. So what are the object that you're taking depends on that. Your characteristic length you can choose, but you need to mention what is the characteristic length. So in such a way, your Reynolds number is governing. So everyone, we need to do at a specific Reynolds number. If you are doing any simulation corresponding to external flow or internal flow, we need to mention this Reynolds number, Re equals to 100 or Re equals to 150 or 1000, whatever it is. We need to mention this Reynolds number only particularly. We don't need to mention what is the density you have taken, what is the velocity you have taken, what is the length of your object or dynamic viscosity. Nothing you need to mention. You need to mention what is the Reynolds number. Only that decides your flow physics. Okay, if you have a question how it is deciding our flow physics, let us see one good example quickly. So everyone can see this chapter, right? See this image. Can you all let me know if it is visible? Is it visible or not?
Visible, sir.
Visible. Thank you.
Visible, sir.
Okay, thank you. I don't think there is a pen option here. So now, just a second. Okay, so here we are having a Reynolds number of 0, approximately 0. It is not exactly 0. Is it visible still? If the Reynolds number is 0,
no, sir. Sir, it is not visible.
it's not visible now.
No, sir.
This is the problem I have. Okay, clear all animations. Let me come out of this thing. Now?
No, sir.
Yes, sir. Visible.
It's visible, I guess, now. Yes, sir, right?
Yes, sir.
Okay. So just have a look at this.
Yes, I guess sir, visible.
Okay. Now look at this Re equals to 0, approximately 0, that you will having a creeping flow. Can someone mute your?
Sure.
I'm
इतना
seeing
जल्दी
some
सर्टिफिकेट भी
noise.
आएगा
Okay. So the thing is here, we are having a Reynolds number close to 0. If your Reynolds number is close to 0, that doesn't matter whether you're using a fluid as air, fluid as a water. If you're setting whatever the velocity, whatever the diameter, the combination of those density or velocity, characteristic length, and dynamic viscosity is coming close to 0, you will have a flow like this, a creeping flow. That means fluid comes, attach the fluid, attach the object, and moves around the object and moves steadily, like a steady, no wake. Wake means these particular things we call as wake. Uh, the portion behind the object we say as a wake with reduced velocity, and any kind of vortices kind of phenomena that we can also see in the wake. Okay, so if you are having a Reynolds number in the range of 3 to 4 and the Reynolds number between 30 to 40, we can see the Reynolds number range. You will get a steady symmetric separation. This particular the image what you are seeing here, this kind of wake. That means you will get a two circulations. Flow circulates here like this, and it will flow. The remaining fluid pass like this. Okay, and the third one is 30 to 40 and between 80 to 90. Okay, in this particular range you will get the phenomena like this with the same, same as above, but the wake is started oscillating. You can see there is an oscillation. Same if you further increase the Reynolds number. Let's not we're going to very high. We shall restrict ourselves to some particular Reynolds number, say 1000. So up to 1000, you can now see what are the different types of wakes. It doesn't matter what is your velocity, what is your density, what is your characteristic length and viscosity. It only depends on the ratio of those parameters. So if the ratio of those parameters lies in this particular Reynolds number, then your flow definitely be any one of these patterns. Flow is definitely behaving any one of these patterns. Okay. So this is the important thing that you should learn, that you should take a note of this, and whatever the Reynolds number that we are going to apply in the simulation, that we should calculate on the beforehand. Let's now calculate the Reynolds number region. Take a snapshot of this and please save this. And later, after completion of the simulation, you can validate that whether you are getting the similar kind of pattern in your flow or not. Everyone, please take a snapshot of that. And finally, you can justify yourself whether you are getting the same flow physics or not, and whether you are doing a correct simulation or not. Okay, please take the snapshot. These are the experimental results, not not the simulation one. Experimentally, people done these things and they finalize these results. Okay, so now let's calculate the Reynolds number that we are doing in our that we are going to do in our simulations. So our circle having a, what is the diameter of our circle?
5 meters.
Diameter equals to 5 meters. Okay, this is a circle and diameter having a 5 meters. So can you?
So diameter is 10 meters. Sir.
Yeah, thank you, Aman. Diameter is 5 meters.
Sorry, sir, 10 meters. The radius is the 5 meters.
Diameter is 10 meters.
Yes, yes, sir. Radius is 5 meters.
Okay, sir. So, yeah, can you please unmute? Someone mic is on. I'm hearing a lot of noise. Yeah, thank you, sir. So here it is 10 meters diameter, and let's say velocity is, let's not define the velocity yet, and let's define the medium. What is the medium that we are going to use is the water. So to define the water, let's assume the water density as 1000 kg per meter cube, and it has a viscosity of 1 by 1000 kg per meter second. Okay, so this is the dynamic viscosity. So let's assume that it has a viscosity mu equals to 1 by 1000 kg per meter second, and density equals to 1000 kg per meter cube. These are details of water. Water at normal temperature and pressure. Okay, water at normal temperature and pressure, let's assume the density is 1000 kg per meter cube and mu is 1 by 1000. This is for simulation purpose. You no need to worry about why we are taking water, why can't we take air. You can take any fluid, any Newtonian fluid. Newtonian fluid has also specific conditions why why I'm saying a Newtonian fluid. You can take any Newtonian fluid such that your density you need to identify, and what is the viscosity you need to identify, and your um, diameter also you need to identify. And then what is the velocity also, v infinity. Okay, now let's take this v infinity as a floating parameter. Let's look into this one. So for validation purpose, let's take one particular pattern. Let's take the pattern of this has a good range, I think. What pattern we can take? Let's try to take this pattern of 30 to 40 and 80 to 90, pattern number 3. So I will select I want to select the Reynolds number as 50. Okay. So let's say the Reynolds number is 50. If Reynolds number equals to 50, what is my velocity? What should be my velocity of the flow? So the equation is Re equals to Reynolds number equals to density times velocity times this is density times velocity times diameter by viscosity. Can you quickly tell me what should be the velocity if the Reynolds number is 50? Reynolds number is dimensionless, so I'm not putting any units for the Reynolds number. So what should be my velocity if my Reynolds number is 50? Can quickly someone calculate and tell me that? Anyone? You can also text in WhatsApp if you are doing it on the other side. What should be my velocity? Can someone calculate the velocity and tell me that? Is it just simple mathematics and it's not a big deal for you all? Any data is missing? I think all the data is available. The diameter is 10 meter, viscosity is there, density is there, Reynolds number is available. So what is the velocity?
Sir, velocity
Yes, sir.
is 5 into 10 to the power minus 6.
5 into 10 to the power minus 6 meters per second.
Yes, sir.
Yes, sir.
According to given data.
So according to given data, you are getting 5 into 10 power minus 6 meters per second. So I feel it is very
Yes,
too low. Let's not go into
Yes,
this
sir.
because of
Yes.
extreme.
Reynolds number.
Okay. So let's not go into this extremely low value. What shall we do? Because if you are increasing some parameter, then it will be problematic like this. 50, extremely low value, right? Let's take,
Sir, we can change the value of mu, dynamic viscosity.
we can change the value of mu also, sir. Let's take, what about the air? If I take these parameters, rho equals to 1.225, I'm taking air as a medium, and mu is equals to 1.7984 times 10 to the power minus 5 kg per meter second, and this is kg per meter cube. This is the corresponding to air. Okay, so take these two as for air and Reynolds number as 50, then what will be the velocity? This is 1.225. Take air as a data, and can you please tell me what is the velocity? Is it much smaller or much larger?
It's the 7.3.
Velocity of air is coming to 7.3, sir.
Yes, sir, yes.
So I did not calculate that. So I suppose it should be maybe supposed to be around 7.3. So let's take this is a reasonable value, because why I am avoiding this extremely low values is it's not correct to use this kind of floating decimals in software or any code of simulation. So we will see those things maybe when we get good experience on handling the softwares. So let's take the velocity as 7.3 and fluid as a medium. So our medium is fluid. So fluid medium is air. Air with this density rho equals to 1.225, and density rho we know, velocity we know, and temperature. Sorry, no need of temperature. We are not going to handle the temperature in these governing equations. We are keeping the temperature as constant, and viscosity we know. Pressure also we know. We set it as atmospheric pressure at the inlet, and pressure outlet. Sorry, pressure inlet and pressure outlet boundary conditions also we will set soon. Okay, fine. And the Reynolds number should be 50. If you've done simulations correct, if you are doing your simulations, that we will going to do simulations soon. If we are doing our simulations correct, then we will get a pattern, the third pattern. Okay, onset of Kármán vertex street. We say it as onset of Kármán vertex street, that is still laminar, unstable, wake. Okay, so if it is clear, can someone also quickly do for the second pattern, because it is a study? We can also look at both the study. Some few people can work on the study kind of pattern, and few people can work on that study pattern. Can someone quickly do for the Reynolds number of 20? If Reynolds number is 20, what is the velocity of the flow field? Take the air as a medium.
So it's coming 2.93 into 10 to the power minus 5 into 10 to the power minus 5.
Sorry, what is the value?
2.9.
2.9 meters per second. 2.9 meters per second, right?
Yes, sir. Yes, sir.
Yes, sir.
Okay, 2.9 meters
Into
per
10 to
second.
the power minus 5 also, sir. Into 10 to the power minus 5.
Are you sure?
No, sir, no.
Only
on the 2.9.
Sir, only 2.9 meter per second.
1.7 into.
Please do not confuse me. I believe Manju sir is saying it is 2.9. Abhishek or someone someone also confirm. Aman is also confirming that it is 2.9. Abhishek, can you please check with them?
Sir, what is the value of the mu?
Mu is 1.7894 into 10 power minus 5.
Sir, it's 2.9
Yes, sir.
Sorry?
Yes, sir. Here is 2.9 into 10 to the power minus 5, sir.
2.9 into 10 power minus 5. Okay, so this is also very low value, sir. So because
Okay, sir.
we
In
use
the
the diameter.
same case, in the last time I have calculated the velocity with the 1.7984. I have not considered the 10 to power minus 5.
Okay, sir, got it. I understand. So
Sorry, sir, for that.
what?
I have forget the 10 to power minus 5.
Okay, sir. Fine. Then that is not an issue. So what we can do is, I just want to every number as a reasonable. Reasonable means in the such a way that it should not go extremely low values like 10 power minus 4, 10 power minus 5, like that in extremely low levels. We will use a standard fluid. We will not change those things. We have a provision to change those things, but let's not change those things as we use the same Newtonian fluid. We have another provision to change the diameter, the geometry what we are taking. So let's take the water. Still, let's take the water again. This is the final calculation that we are going to do. You will be ending up here today. 1000 kg per meter cube, and mu equals to 1 by 1000 kg per meter second, and diameter d equals to 0.1 meter, and velocity v equals to. Can you quickly find it out? It's not still. No. Let's take it is as 0.0 1 meter, and R equals to 50, A equals to 1000 kg per meter cube, mu equals to 1 by 1000. Can someone quickly do that? If diameter is this much, what is the velocity in these two conditions? What is the velocity in first condition? If Ra equals Reynolds number is 1000 and the material is water.
For the first case, sir, it's 0.02.
For the first case, it is 0.02. 0.02 meters per second. Okay, who is this? Pragya. Okay, what is the next one? Maybe 0.05. Is it?
Yes, sir.
0.05 meters per second. So these things are reasonable. You see, these are in the limits of 10 power minus 2, 10 power minus 2, 10 power minus 3, 10 power 3, and 10 power 1. So everything is in below 10 power minus 3 or in the order of 10 power 3, 10 power 3 to 10 power minus 3. So let's take these two conditions for our next simulations. I request everyone to please confirm these values. Is these two values are correct or not? Are these values are correct? Aman, Abhishek. Can someone quickly confirm it? Hello. Am I audible?
Yes, sir.
Okay. They have they don't have a network. Yeah, others are also there.
Sir, just give me a second, sir.
Okay, if you have any problem with the network, just text me in WhatsApp. Others, if these values are correct, then we can proceed for tomorrow's next session. Whenever we have the next session, we are going to apply these things. We will be setting our fluid as a water and applying this velocity. And we also need to change our dimension to 0.01 meter as a diameter. We already did created our geometry, so we need to follow the changes approximately that we calculated now to get this Reynolds number. So we are going to change the diameter in our geometry, and we are going to apply this velocity for getting the Reynolds number of 50 and getting the Reynolds number of 20 in our simulations. We will do both the simulations and we will see whether the patterns that experimentally people see, whether the same patterns are we are getting or not. Okay. So I believe everyone.
Sir, velocity may be 0.005, sir.
005.
Velocity is 0.005, sir.
005 and 0.002. Is it right, sir?
I have calculated only the second part. You can find out 0.005 for the Reynolds number 50.
Okay, sir. Others, can anyone others also confirm that it is just a normal calculation? So 20.
Yes, sir. It's 0.005, bro. Or
It's 0.005.
minus 3.
Okay, still it
Yes,
is
sir.
fine because it is in the order of 10 power minus 3. So if it is in order of 10 power minus 3, still it works for us. So no need to worry about it. So we are going to set up these conditions. Okay.
Okay.
Sir, you are muted. Gangadhar sir.
Okay. Is it okay now?
Yes, sir.
Hello. Okay.
Yes, sir.
So thank you all for joining. So I hope you all understood what is the importance of Reynolds number. I thought to start the simulation today, but as you asked other important queries, I hope you also learned those things. So maybe in the next session, we will apply these conditions and we will directly jump into the simulations using Answers Plane. If you are also following the same content in the next session, we can maybe you may see the patterns in the next session itself. Okay. So thank you all. If you have any queries, you can send it to me in WhatsApp or mail. Better not WhatsApp. You can list your queries and we can discuss those queries in the next session, in the coming session. Like that, you can plan with Arhit also, or you can write down your queries and we can discuss in the next upcoming session. So any one or two quick questions, then we can end up this session.
Sir, I have one question, but not like related to this. Adit, sir. Adit.
Yes, Arhit.
Sir, actually, sir, shall I discuss it right now or we can discuss it later, sir?
If it is not related to this, we can discuss it later on.
Okay, sir. Actually, in tubercles, I had some doubt.
Yeah, we can discuss it later on. I will give you a call in the evening.
Okay, sir.
Okay. So any further doubts related to the concept? Aman, Abhishek, Pragya, Ravin, Manju sir. Okay, if no queries, Ajoy. Okay, thank you all. Thank you for joining. I will upload this session. You can look into it if you have any questions.
Okay, sir. No queries.
Thank you.
Today's session was very valuable and very good, sir. Thank you, sir, for that.
Thank you, sir. Thank you so much. Bye all.
Thank you, sir.